Okay. I guess I should start class with a reminder to the nearly half the class is not here, but yes, attendance still does count for a certain part of your grade. Okay. Now, a couple other things that I want to point out. First, as faculty advisor for the science student chapter, just let you know that tomorrow there is an event we're holding. A career panel, so that's tomorrow from 4:30 to 5:30 in the International Center 101. So I'll be taking part in a panel of people with a variety of mathematical careers or various stages of those careers. So anyone interested in mathematical careers wants to find out what opportunities there are out there and how to get into them. That's what this is about. So feel free to come and join us. You might have seen some emails about this already. Okay. Now, one thing that I wanted to mention, well, I was going to mention this on Monday, but I thought, oh no, there'll be more people here today. Silly me. But anyway, one thing I've noticed in the homeworks from a number of people on the, particularly on the reading questions, when it comes to homework, I'm fine with you all working together. I think that can be very helpful to do that. But like any of these things, it's only really a good thing if it's done properly. And properly does not mean simply one person writing something down and the other person copying it. I've seen instances of that happening, but also copying it incorrectly. What that says to me is you don't understand what you're writing. And that's kind of a point, is to get a better understanding of the concepts behind the methods that you're using on the textbook exercises. If you don't know, that's when you take advantage of your resources, the notes, the textbook, me, or anything else that you can find. When I was a student, I used whatever resources there were out there, and there were a lot less back in the late 80s and early 90s. In fact, the World Wide Web did not exist yet. So YouTube was still like over a decade off. So in that case, I had to rely more on a textbook. I went to the professor's office hours. We're required to, in this department, hold 10 per week. And it ends up just being time it ends up being used for something else, and it's not how it should be. So if it's not convenient to come, then you can email me questions, whatever. Take full advantage of what you're shelling out a lot of money for. Because all too often what happens in classes like this is students treat the material as here's a bunch of recipes to follow. For this problem, use this recipe and so forth. Follow this procedure. Often doing so blindly without taking the time to think through it. And that's one of the reasons why I give things like reading questions to get you to stop and think about the concepts a little bit more, about where all these things come from, how they relate to one another. And that's why I'm going to enforce this to a certain extent on the final exam. So I've done this years ago, but not lately. So the final exam is going to consist of two parts. The first part will be what you're used to. The kind of problems you see on the other test, the kind of problems you see from the textbook. And that'll be on the new material. What I'm covering this week, stuff since test 2. And then next week on Laplace transforms. The other part is what I'll refer to as a lightning round. There's going to be a whole bunch of questions that are similar to reading questions. Short answer, and that takes me to another thing. Reading questions are meant to be short answer for the most part. Just a few lines, paragraph at most. But sometimes I get an answer that takes almost a full page for one reading question, and I'm hunting in there, like, where's the correct answer? Like, oh, there it is. So I'm looking for one tree in a very thick forest. So for future reference, for reading questions, keep it brief. And that's the idea on the final too. And you would not have to be able to answer every question. I would say answer X number of questions out of however many I put. And I will put out a practice version, just like I do for VEver tests, to give you an idea as to what you're in for. So that's going to count for half of a grade on the final. In fact, your best way to study is by looking at the reading questions or certain parts of my notes. I'll have more to say about that as it gets closer. So you'll have an idea as to what you're in for. But I just want to let you know up front, with a few weeks to go, that that's what I'm going to expect. This isn't about just, here's this problem, follow these steps. So you have been warned. Okay. Now, even though this is a differential equations class, what you need now is a linear algebra lesson for the kind of differential equations that we're about to look at. On Monday, we looked at higher order equations. But on Monday, we only looked at ones that were homogeneous. Now we'll take a look at non-homogeneous, but still linear equations. Just like with second order equations, you have two options on how you can solve them. First, there's undetermined coefficients. And there's really nothing to cover with that method. It's exactly the same as for second order equations. I will do an example like on Friday, but really where time needs to be spent is on the other method. What is the other method for non-homogeneous linear equations? Variation of parameters. And that gets a bit more involved because as you move to higher order equations, because of the linear algebra involved. So here's our general nth order equation. So nth derivative, call this notation from Monday, P1 yn minus first derivative plus P2 yn minus 2 derivative. And I'm writing this P1, P2, etc., but we don't have to assume they're constants. I'm just being lazy, just this once. So it could be, you can think of this P1 of t or P2 of t. The method for various parameters is exactly the same anyway. Y prime plus Pn y is equal to some function g of t. All right. We assume a form, and as with second order equations, we're going to assume that y1 of t, y2 of t, and so forth up to yn of t, that those are solutions of a homogeneous equation. In other words, where g is equal to 0. So then you, just like in second order equations, you assume that the particular solution that you need has this form. Well, how do we express the particular solution in the second order case? You just dealt with that in the test and recent homework. So start it off. What is the form of a particular solution from the second order case that you use for variation of parameters? I know y'all wrote it down various times. What?
Is that C1 e to the...
Almost. That's a homogeneous case. Yeah, so now we're just dealing with a particular solution. So instead of C1...
W.
Right. Yeah, W1. Okay. And then what would follow it? Yes.
Y1.
Yes, Y1 of t. And then continue.
W2.
Yeah. All right, that's what you have for second order. So you just continue it. You have n terms of this form. So now you have. So now instead of 2 terms, you have n. And just like in second order case, where you find your w's is by integrating, but it's getting the integrands that's going to be more of a pain. And so what happens is, just like in the second order case, the derivatives of your w's, w1 prime, w2 prime, etc., all satisfy a system of linear equations. Whoops. Okay. And in the second order case, it was just a 2-by-2 system, so we could just work out what the formula was. And so it was not really obvious that it's really what you were doing, but there's no escaping it in this case with more variables. Okay, so your derivatives, w1 prime, w2 prime, so on, up to wn prime, satisfy this system of equations where you have y1 w1 prime plus y2 prime and so forth, all the way up to yn wn prime is 0. And then you have y1 prime, w1 prime plus y2 prime. So as you go from one row to the next, it's still w1, w2 prime, but that stays the same, but your y's get differentiated. And your right-hand side is still 0. You keep going. Second derivative. All the way down to the last rows, I'll just fill in the last 2. So we have n minus 2 derivative of a y's, still times y times w1 prime, w2 prime, etc. All the way down to yn, n minus 2 derivative, wn prime, that's still 0, everything's 0, until we get to the very last row. So y1, n minus 1. So your coefficients are your n minus first derivatives. And this time it's equal to g of t. All right, so variation of parameters really is about solving this system of equations for w1 prime, w2 prime, and so forth, and then you integrate those to get your w1, w2. And whether you knew it or not, I covered it very briefly, but that's what you were doing in the second order case, solving a 2-by-2 version of this. So now if you had a system of n equations and unknowns, what you learned if you took linear algebra is you would use your Gaussian elimination and substitution. We're not going to do that because that's enough of a pain to do with numbers, but what you have here are functions. You need I'm trying to get a formula for a solution, so you need a formula for a solution of this system of equations. So this is of a system of equations of a form ax is equal to b. This is a generic way in which everybody writes a system of n linear equations and n unknowns. Just that in this case, your unknowns, x, consist of your derivatives of your w's. Your right-hand side, vector b, is all zeros, except for g of t in the last position. And then your coefficient matrix A consists of your homogeneous solutions, first row, and then you keep differentiating them to go to the second row, all the way down to the n minus first derivative in the last row. Okay. This came up on Monday. We need the system of equations to have a solution. So it will if the determinant of this matrix is non-zero. But as we saw on Monday, that determinant is called what? If your entries come from solutions of your homogeneous differential equations, the name we give to that determinant in this case is Wronskian. So we need a non-zero Wronskian. And you saw that in variation of parameters for a second order case. Both your integrals had Wronskian in the denominator, so it had to be non-zero. Okay. So what we need to deal with now is, how do we solve the system of equations when all of your entries are functions? Okay, and for that we have what's called Cramer's rule, a highly impractical method for solving systems of linear equations. Except if your entries are all functions, it's really the only practical way. It's just that when you get to large system of equations, it gets pretty nightmarish. But in our problems, you'd be doing something of maybe third order, fourth order, something like that. So for small matrices, it's okay. But Cramer's rule. I don't suppose this was covered in linear algebra, in 326? No? Okay. I'm not sure why I bothered asking. Okay, so the solution of this system of equations, ax is equal to b, is given by this formula. So each entry of your solution, so xj, so for j equals 1, 2, up to n, is equal to the determinant of a sub j, which I'll define in a moment, divided by the determinant of a, and in this case, that is just your Wronskian, so that part is no different than the second order case. So the aj is a matrix obtained by replacing column J of A with your right hand side B. So what I'm going to do in this case is I will give you formulas for your W1 prime, W2 prime, etc. Based on this rule, and then we need to talk about, so you can see what it is you need to take the determinant of, but we also need to talk about how you do determinants. You may have done the computer determinants before, and 2 by 2 comes up fairly often, but what about something higher order? And I'm sure that was covered in linear algebra, but I'll make sure you remember. So in this case, let's suppose that n is equal to 3. Then your matrix consists of your 3 solutions, y1, y2, y3, their derivatives in the second row, and then your second derivatives in the last row. Your right-hand side, b, is 0, 0, all zeros except the last element is g. And then your vector of unknowns is w1 prime, w2 prime, w3 prime. So that's what you need for variation of parameters. So, using Cramer's rule, you say that w1 prime, well, the denominator is just going to be Wronskian of y1, y2, y3 in all cases. So the determinant that you need for your numerator, and keep in mind the vertical bars, so I'm using these big square brackets to indicate, here's the matrix. When it's vertical bars, that's a shorthand for determinants. So I could have easily written this as determinant of A over determinant of A. Same idea. Okay, so it doesn't mean absolute value in this case. Not when it's a matrix. So what do you do for W1 prime? J is equal to 1. So you take your matrix A and you replace column J of it, so the first column, with your right-hand side vector B. So it's going to be 0, 0, G. And then the other two columns stay as is. Y2, Y3, Y2 prime, Y3 prime. Okay. So what you would do is you would compute those two determinants. Fortunately, having the zeros here is helpful. That drastically reduces the work. And then, so really it boils down to a 2x2 determinant instead of a 3x3. And then your Wronskian. And once you worked all that out, simplify as much as you can. And keep in mind it generally does simplify a lot, just like in the second order case. Then you integrate that like you did before. Now, let's see if you can do W2 prime. You have Wronskian down below. So what should the matrix entries be? You go by columns. First column, second column, third column, from left to right. What should I fill in here? J equals 2 now.
You said what equals to?
What?
What equals to?
J. So applying Kramer's rule. So basically you're doing this. So you start from here, but you replace the appropriate column with the vector V. And you want to take a shot at it.
First column would be y1,
Uh-huh.
y1 prime, y1 double prime.
Okay.
The second one would be 0, 0,
Yep. And finally?
y3, y3 prime.
Yeah. Okay. Y3, Y3 prime, Y3 double prime. Okay. And then finally, for W3 prime, Wronskian down below. And what do we put up top?
Y1, Y prime, 2, 1, Y double prime,
Sorry, repeat.
Y prime 2, Y prime 1.
Yeah. Y1 prime.
Yes. Y1 double prime.
Okay.
And then Y2, Y prime 2, or Y2 prime.
Yes.
Yes. And 0, 0, G.
Okay. All right. So those are the three determinants you would need. So for an n-photo equation, you have n plus 1 determinants in total to compute. You have your Wronskian and then your n numerators. So any questions at least about setting up determinants before we talk about actually computing determinants?
What exactly is G in that case?
Oh, G is the right-hand side of your non-homogeneous equation.
Okay.
Yeah, because we're only going to use this for that case. Okay. Now, so 3 by 3 determinants are a nice special case. There's a trick that applies only to them. Actually, I can never remember the name of it. I'll have that too. Unfortunately, the first several Google results are not popping up. Okay. This one even has the trick, but they don't give the name. All right, never mind. tell you find it. Like rule of Saturn or something like that. Some weird Vulcan-like name. Okay, so the first, we call for a 2x2 determinant. Yeah, A, B, C, D as your entries. So using vertical bars to indicate determinant, and that would be AD minus BC. Now for a 3x3, the determinant of, so I have ABC first row, DEF second row, GHI. What you can do is, if you repeat the first two columns, write them off to the right side, like that. What you do is then draw diagonals, first from upper left to lower right, and then upper right to lower left. And what you do is you multiply the entries along all 6 of these diagonals. The ones that go this way, from upper left to lower right, you add those. The ones from upper right to lower left, you subtract them. So you get AEI plus BFG plus CDH minus CEG minus AFH minus BEI. So I'm just reading the entries off of these diagonals. And what's going to happen for your numerators is in one of these columns, 2 of the entries will be 0. So that's going to knock out some of these terms. So that'll make your life easier. Now, in general, so we go to 4x4 case. I'm going to, since this trick doesn't apply, I'm going to write this out in a way that lets you see what the general pattern is. So what you do is you can go across any row or column. I'm going to use the first row because keep in mind, determinant of a matrix is the same as determinant of its own transpose. So, sorry, if you switch the sets of rows and columns, it doesn't change the result. So that's one thing that's convenient. So if I go across the first row, I'm going to have A times the determinant of the matrix you get by deleting the first row and first column. So that'd be FGH, JKL, NOP. And then as you go across the first row, you alternate signs. So minus B, and now you take a matrix you get by deleting still the first row, but now the second column. So this one is no longer deleted. So you have E, G, H, I, K, L, M, MOP. Okay. And then you keep going across the first row, alternating signs. Now it's plus C, and now you delete the first row and third column. So that'd be, someone tell me what it would be. So forget the first row, forget the third column, and what should go in here?
Even IKL.
No,
IJL.
IJL, yep.
M, N, P.
M, N, P. Okay. All right, so now who can tell me what is the last term? So this part is done. What? Minus D. Okay, and what gets filled in here? And oh. All right, and that's it. But now you have 4 3x3 determinants to compute. Again, at least for your numerators, having some 0 entries will help matters. But yeah, it's going to be pretty tedious. Bless you. Okay. Now, if we take a look at, for instance, one of the questions about this one. If we look at, for instance, for W1 prime, over here, instead of going down the across the first row, you might as well go down the first column. Again, doesn't change the result. So you'd have 0 times the determinant of this minus 0 times the determinant of this matrix. And then all you would have is, so I can actually write it down here. The determinant of this would just be G times the determinant of a matrix you get by removing the first column and last row. So that would just be the Wronskian of these two. So G times Wronskian of y2 and y3. Now, I can do something similar over here. Now, so what would happen is I have a confession to make. I don't remember a rule off the top of my head for going across any row or any column. But what I do remember is if I take my matrix and swap any two rows or any two columns, the determinant changes sign. So this is not exactly like this case because the advantageous column is the second column, not the first. But if I swap columns to make this one first, then with just a sign change, I can be back in this situation. So the determinant of this matrix would be minus G times the, and so now I have these two columns swapped, and I have a Wronskian of y1 and y3. Okay, so similar to this, just a sign change. And then finally for this one, what I'd like to do is have this column first, followed by the column of all the y1s, and then all the y2s. Because what I could do is I could just swap these two, but that so that would give me minus G Wronskian of, but not, it's not y1, y2. If I move this over here, I actually have Wronskian of y2, y1. And when you rearrange your functions in your Wronskian, can change the sign. So the other thing I can do is I can just interchange these and I get another sign change. So the sign changes back to positive. G Wronskian of y1 and y2. So in this 3x3 case, you can express your numerators that way. So at least you reduced a 3x3 determinant to a 2x2. You have the same kind of Wronskians you did in the second order case. So that's a shortcut for you for third order. Something similar would apply for fourth order equation. W1 prime would be equal to G times the Wronskian of y2, y3, y4 over the Wronskian of all of them. And so on, with W2 prime, etc. But you would end up alternating signs, just like what happened here. So that's one way to cut down the size of your determinants. So at least for a fourth order equation, you'd only have one full, nasty fourth order derivative to compute. That would be Wronskian-Wire solutions. So questions about these determinants? So, tedious homework coming your way. I know, as if it wasn't tedious before.
Did you say we were gonna run into the fourth order one right there? Did you just
Yeah, I don't think you'll have one that's larger than that.
Okay.
Yeah. But yeah, we're definitely like the third and fourth on various homework problems. So in fact, what I'll do now, yeah, I have some time, I'll go ahead and do an example.
So the third Wronskian will equal both of those?
Hold on, what do you mean?
The G, W?
Oh, yeah, either one. Yeah, just functions of different order changes the sign. But yeah, because the thing is, Wronskian of y2 and y1 has them written in the opposite way. So that's the thing to keep in mind there. That's the order in which the functions are written in this notation matters. Okay, and you're going to see that in this example. Okay. Okay, so we have the problem is to compute the general solution of the third order equation, y triple prime minus 2y double prime plus y prime is 1. So who could tell me what is, so this is your g, it's a constant in this case, but what is the characteristic equation? So we need that to get our y1, y2, and y3. So this is from Monday. I know you know how to do this. R cubed.
minus 2 r squared.
Yeah. Okay. All right. So now we need the roots of this. Well, how can we factor it? Yeah, then we take out an r. So r squared minus 2r plus 1. And how does the rest factor?
Plus 1. Minus 2.
R minus 1, R minus 2.
Yeah, it's a perfect square. All right, so our roots are 0, 1, and 1. So we have a repeated root. So if I call this R1, R2, and R3. So so what will my solutions be that come from those roots? They're all real. So what?
We do it like the C1.
Well, no C's.
Oh, there's
Yeah, yeah. What? 1. E to the 0 t. So when it's real roots, it's e to the root times t. So in this case, it would just be 1. Okay. What will the next one be to correspond to these roots?
E to the t.
E to the t.
And t e to the t.
And because it repeats, yes, we need t e to the t. So those are our 3 solutions. So now we can write down our homogeneous solution. And that's where, I've seen this confusion a lot lately, that is where the constants come into play. C1 times 1 plus C2 e to the t plus C3 t e to the t. And then if you were given initial conditions, at the very end of this process, after we get the particular solution, then you would go back and find C1, C2, C3. All right, so any questions so far about the homogeneous part before we get to the variation of parameters part? All right, now for variation of parameters, we need the Wronskian of all of these. So that'd be the determinant of, so you write your 3 solutions. 1, e to the t, t e to the t, across the top. And then you fill in their derivatives. What are derivatives? Yeah, that helps. E to the t. All right, so those 2 are easy. And then here we need what? Unfortunately, product rule. All right, so we're going to get e to the t plus t e to the t. Oops, a little room. And then we need product rule again, so that's going to give us 2 e to the t plus t e to the t. All right. So now we compute the Wronskian of this. But what helps is these 2 entries being 0. So if you, well, you could use that 3x3 trick, but it's actually better in this case to use the general formula I gave for a 4x4 case. You go across the first row, and we take 1 times the derivative of this matrix, because then when you move to the other entries, because of these zeros, you're not going to get anything. So really it's going to be 1 times the determinant of this 2x2 matrix down here. Now, if you're not sure about that, if you could go through a process and see for yourself that these zeros are going to cause all other terms that would arise from the definition to turn out to be 0. Because what happens is the matrix basically decouples. We have these a 1 by 1 and a 2 by 2 block along the diagonal, and when that happens, you can just take the determinants of these diagonal blocks, and that gives you a determinant of the whole thing. Okay, so now we can just take the determinant of this. That's going to be e to the t times this lower right entry here, minus product of these two, and there's a lot of e to the t's. In fact, we could factor out a e to the 2t out of every single term. And we get 2 plus t minus 1 minus t. So everything in here cancels, and almost, and you get 1. So your Wronskian is just e to the 2t. This is what generally happens in the repeated root case. Wronskian of e to the at and t e to the at generally turns out to be e to the 2 at. That's what happened in this case. All right. So we now have the denominator for all of our integrals. We just need the free numerators. And unfortunately, time is running short. I may have to finish this starting on Friday.
Wait, why is it e to the 2t at the end?
Because, well, I factored out this e to the t from everything, and then every term in these had e to the t, so I could factor out 2 of them. They get multiplied together. And then what was left, everything in here is just simplified to 1. So, W1 prime is going to be the determinant of, so the matrix that we have over there with each column replaced by 0, 0, G. So we'd end up having 0, 0, 1 for the first column, and then you have e to the t, e to the t, e to the t, and then t, e to the t. I'll factor this out here, t plus 1, e to the t, t plus 2, e to the t, just simplifying those. Over Wronskian, which was e to the 2t. And then W2 prime, you go back to your original matrix and replace the second column by 0, 0, G, which is 1. So that's where that 1 is coming from. So this matrix is going to have an even simpler determinant because of all these zeros. Divided by your Wronskian. And finally, W3 prime, we replace the third column by 0, 0, 1. And then the other 2 columns are the same as over there, all over e to the 2t. So these 3 determinants need to be worked out. So, so what you could do, for instance, is for this first one, you can, it's just g times the determinant of this. Bless you. So it's 1 times e to the t, actually e to the 2t, t plus 1, minus t e to the 2t, all over e to the 2t. This simplifies because the t's will cancel, and what you're left with is e to the 2t over e to the 2t. So you end up with just 1 in that case for your W1 prime. So like I said, a lot of things simplify when you compute all these determinants and then simplify them. for this one, it's just going to be 1 times the determinant of this matrix because of all the zeros here. So you end up with 1 times 0 times this, which is 0, minus 1 times e to the t over e to the 2t. So you end up with, okay, something's wrong here. Oh, no, I goofed, sorry. This times this was 0, minus 1 times that, so t plus 1, e to the t. So after you simplify as much as you can, you get minus t plus 1 over e to the t. And then finally, for the last one, I know my time is up. Again, it's just a determinant of this matrix times 1. So it's e to the t times 1 minus 0 over e to the 2t. So that's e to the minus t altogether. And so I'll finish this on Friday because we would have to integrate these to finish off the solution.